here we take a look at the analogy for the spring mass system. So here we also assume that this is a wall which is fixed, and then it connects to a spring with a coefficient k, and then it also connects to the mass to an object with mass m. So which means that if we have some displacement x, and then there will be a force acting on it as before. There will be a force F equals negative kx. Okay, which means that if it moves to the positive side, the force will point to the opposite side. Okay, so which means that if the mass moves to the right side, the force will point to the left side. If the mass move to the left side, the force will point to the right side. So we have a negative sign here. Also, we try to model the frictional force. Frictional force, 阻力. The frictional force, we can just model it as F friction to be negative B times dx dt. Or if you're familiar with calculus, you know this is actually negative B times V. Okay, which means that if the velocity is high, the frictional force will be larger. If the velocity is zero, there won't be any frictional force. Of course, it is not that matched with what you consider, because in the mechanics, 你们有那个静摩擦跟动摩擦，但是 so here we only consider the 动摩擦. Okay, so which means that if we have V to be zero, we don't have any frictional force. If this V is larger, the frictional force will be larger. Okay, 越动得越快，它的阻力就越大。这也蛮符合我们的常理的认知的。Okay, so we have this one. Okay, and also we have this negative sign, which means that if we are moving to the positive direction, the frictional force should point to the opposite direction, right? So we also have this F equals negative BV, point to that direction. Okay, so here we can try to write out the free body. So this is a free body. We can try to write out the ODE. So we have F equals, the total force should be negative kx negative B VV is dx dt. Okay, so this is according to Newton's second law of motion. It is ma, F equals ma. So ma, a is the second derivative of the displacement. Okay, so we have this one, and then we try to move this thing to the right side. So we have a m d2x dt2 plus b times dx dt plus kx equals 0. Okay, so we can just divide m on both sides. We will have d2x dt2 plus b over m dx dt plus k over m x equals 0. Okay, so similarly, we can write out the characteristic polynomial, which is s squared plus b over m s plus k over m equals 0, like this. Okay, so similarly, we will consider the case b squared minus 4ac is negative. Okay, so which means that this should have a solution like s equals 1/2 of negative b over m and then plus or minus square root of b squared minus 4ac. B squared is b squared over m squared minus 4k over 4k squared, 4k over m, 4ac, 4k over m, like this. Okay, so we can just distribute this 2 to here and then inside. So, and then also this thing is negative, so we try to make it like negative b over 2m and then plus or minus j square root of okay, so we move it to the front. Okay, so we have k over m minus b over 2m and then quantity square. So which is similar to what we got for the RLC circuit. Here, this is the omega square. This is the omega square. This is the coefficient. So the oscillation will be like x equals, we have the amplitude, or the amplitude, like this is just a, and then exponential to negative b over bt over 2m. Okay, this is the real part, go to here, and then the imaginary part, this is omega prime, so becomes a cosine of omega prime t plus phi. Okay, so for the spring mass system, you will have a similar thing. And then originally, if we don't consider the frictional force, omega should be like square root of km, which is actually this thing. Okay, here, as much as we have some frictional force, then so and then this omega prime will be slightly smaller than omega. Okay. Okay, so here we have a sample problem. So it says a series RLC circuit has inductance L, capacitance C, and the resistance R, and began to oscillate at time t equals 0. At what time t will the amplitude of the charge oscillation in the circuit be 50% of its initial value? Note that we do not know the initial value. Okay. Yeah. So so the idea is that it will have a form of a Q equals maybe I use the blue color. Q equals capital Q exponential to negative RT over 2L cosine of omega prime t plus phi. Okay, so this is the general form. Okay, so the idea it asks is what is the 50% of its initial value. So actually we just ignore this part because it is just like something like this. It is something like this is exponential Q exponential to negative RT over 2L, and then we have the flipped one now. The symmetrical one. This is negative Q exponential to negative RT over 2L, 2L, not 2T, 2L. Okay, and then we will have the oscillation. This is the practical one. Okay, something like this. Okay, so you can check. This is the period. This is the period t equals 2 pi over omega prime. Okay, so it will be something like that. Here, of course, I just take the phi to be 0, so that at t equals 0, it just go to the maximum point. Okay, so here the point is, it asks you what is the time when, of course this is Q, when does it go to half of Q? Okay, it asks you what is this time. So we don't necessarily need to know what Q is, because we only want is this term to be 0.5. Okay, so the point here is we try to make exponential to negative RT, let's say 0 over 2L to be 0.5. Okay, so we can take the reciprocal on both sides so that the exponent become positive and then it becomes 2 and then take the lateral on both sides. So we have a RT0 over 2L equals lateral log of 2. Okay. We just take the reciprocal and then take the lateral log. Okay, so we have a T0 equals 2L over R and then natural log of 2. Then we can just plug in the number. 2 times L, L is this one, 12 times 10 to the negative third power. And then over R is 1.5 ohm and then times natural log of 2. Okay, so this value is nothing but 11 millisecond. 11 millisecond. 11 millisecond. Okay, for part B, it asks you how many oscillations are complete within this time. How many oscillations? So just now we already got this figure like this. Okay, suppose this is T0. It asks you how long does it how many oscillations. One oscillation means one period. Okay, this is the period. Okay, which means it asks you T0 over T. What is this value? Okay, so actually we would like to want to find this value. Of course, this T is related to the omega prime. So let's try to calculate omega prime first. Omega prime is actually square root of 1 over LC. This is omega square, 1 over LC minus R over 2L and then quantity square. So we can just plug in all the values. Okay, so square root of this 1 over 12 times 10 to negative third and then times C is 1.6 times 10 to negative 6 minus R is 1.5 over 2 times L. L is also 12 times 10 to negative third and then quantity square. Okay, so omega prime is 7.217 kilo radian per second. Okay, this value. Okay, so it means that the number of oscillation should be T0 over T. T0 over T. So this is the time for one oscillation. This is the total time it takes for the amplitude to drop by 50%. Okay, so this T is 2 pi over omega prime. Okay, so we can just plug in here. So we have T0 omega prime over 2 pi. Okay, so here we have T0 is 7.217 times 10 to the third power times omega prime. This is omega prime, and then T0 is this one, 11 millisecond. 11 millisecond, 10 to negative third power, and then over 2 pi. So this value is 12.6. 12.6. Okay, of course there is no SI unit here because this is just a number. How many? Yeah. So actually there are 12.6. I just draw it like 2. So it decays much slower than this. But if I just draw too much and then it just like a solid object, so you cannot really know what it is. Actually, it takes a long time to decay to this half of the amplitude. Okay, so next we talk about the phaser, the phaser. Okay, we will talk about the phaser for RLC. I think at least in my high school physics I already learned phaser, but at that time I don't really know what phaser is, because phaser is a very strange thing. Phaser is actually related to the Fourier transform. But actually in high school you have no way to learn the Fourier transform. Even for bachelor student, you still consider Fourier transform is very complicated math. So yeah, so even when I learn the phaser in my year 1, I still consider it is so strange. So strange, but I try to explain it as at all of my effort. Okay, so so here we consider we have a resistor, and then this is a EMF, but this EMF is a so-called a alternative EMF. Okay, you should have known something called DC or AC. DC or AC. DC means direct current, 直流电, and then AC means alternating current, 交流电. Okay, so this is 直流, this is 交流. So here this one is a AC, it's an AC source. Okay, it's an AC source. So usually when I draw a DC source, I usually draw it like this: a circle with plus or minus sign, and then I draw V, just say VS, something like this, to specify this is a DC source. And if I need to draw a AC source, a circle with a sinusoidal inside, so this is an AC source. Okay, yes, of course you still need to consider maybe this one is positive, this one is negative, then the polarity. But actually it's hard to define the polarity of a sinusoidal, because a sinusoidal goes from positive 1 to negative 1 back and forth, so it's still not, but if you just fix the time, so you can say consider this time this is positive, or if something like this, this is positive, this is negative. Okay, but anyway, here we consider this EMF is E equals EM is the amplitude of the AC source times the cosine omega dt. Okay, for instance, in Macau we have a so-called 220 volt. Okay, so this is a root mean square value. Actually I have not mentioned root mean square value yet. Later in this chapter I will also mention what is root mean square value, but at the moment you can consider the amplitude. The amplitude should be EM should be like 220 times square root of 2, should be like 310, or I don't really remember the correct number, like 310 or 300 and something. So this is the amplitude in Macau. The amplitude is like 300 something, but we mentioned it at 220 is the root mean square value. And in Macau the frequency is 50 hertz. I remember correctly, it's 50 hertz. So the angular frequency is 2 pi times 50. Okay, 100 pi. Okay, so here we assume that this is a AC source. We have E equals EM cosine of omega dt. Okay, so this is the frequency of the source. Omega d is the frequency of the source. So in that case, we just have this AC source series with a resistor only. Okay, so this very, very simple circuit. You will consider, why we need to consider such a simple circuit? But we just let you familiar with this kind of things. And later on it becomes more complicated. Okay, so here we have this one. So which means that VR, let's say this is VR V out should be actually the same as E. So V out should be EM cosine of omega dt. Okay, it's just like stupid thing. Okay, these two are the same. Here we try to define something called the phasor. The phasor. So actually, this one is a phasor. This one is also a phasor. Actually, later on, you can still, yeah, this is actually a complex number. Okay, why we need the phasor? The phasor means we try to use a complex number. You try to use the complex number to represent a sinusoidal. OK， 用一个复数的数字去代表一个正弦波。Okay, so as you know, a sinusoidal should have an amplitude, and also the phase. Okay, it consists of two parts for a single frequency sinusoidal. Okay, it should have an amplitude and phase, 正负跟相位. Okay, so if we just represent this sinusoidal, of course this sinusoidal is a time function, so it should be like a amplitude. This is the amplitude, and then of course here the phase is 0. Okay, so here we try to represent it with the, so we just put this amplitude and phase as the complex number. For the complex number, it will be like the amplitude E exponential to j phi. If you still remember, this exponential to j phi, according to the Euler's identity, is cosine of phi plus j sine of phi. Okay, so we can actually use a complex number to represent a sinusoidal. It will make things easier. It will make the calculation easier. Of course, the mathematics behind is a little bit complicated. It's related to the Fourier transform. But the point is, calculating the complex number is easier than calculating the differential equation. Because you can consider something like this. If we have a circuit, if we have a second order circuit, and then if we have a sinusoidal input, let's say this part. If we have a second order circuit with a sinusoidal input, let's say we have V d2v dt2 plus a times dv dt plus bv equals a times cosine of something. Okay, so this is the input. This is the EMF, or the EMF, or the source, or whatever. Okay, so this is the AC EMF, alternating EMF. Okay, and then we have a second order RLC circuit. Okay, so when you just learn how to solve the differential equation, you need to make the right side to be 0. We try to solve for the homogeneous solution, and then we try to assume the particular solution, like let's say C1 cosine of omega t plus C2 sine of omega t, and then plug it in, and then you try to find C1 and C2. And then you will have the complete solution be like V equals something like let's say C1 and then exponential to negative something t, and then cosine of omega t plus omega prime t plus phi. Okay, so this is the damped oscillation, and then plus a C2 cosine of omega t plus C3 sine of omega t. Okay, so it will take lots of steps to calculate this value, this phase, and then these two value. You feel, this is really complicated. The idea for using phasor is that we may not very concerned about this part, because if this thing is negative, this term will tend to 0 for after some time. Okay, this is attenuating. Okay, after some time it will tend to 0, but this part is still a sinusoidal. It will run forever. It will run forever. This cosine part will run forever. So maybe we will more concerned about this particular solution. So the phasor will give you a much quicker way to find this value, or maybe you can just change it to R cosine of omega t plus phi. Okay, we can quickly find R and phi. Okay, these two will be represented by a complex number. Okay, you just try to calculate some complex number. Okay, without considering the calculus or the differential equation, you just play with the complex number, and then finally you get a complex number, and then you just convert it to a sinusoidal. So the idea is something like this. Hope you can accept this. Okay, so here the idea is, yeah, as much as we have VR, we also have IR. IR should be like VR over R cosine of omega t. This is nothing but the Ohm's law. Nothing but the Ohm's law. Okay, so here, okay, in some sense, VR is this capital VR. The phase is 0. So this is this can be represented by a complex number VR, although this complex number is a real value VR only. Okay, so but at least you can consider VR is a phasor, and then IR is actually this thing. IR is actually this thing, and the phase is also 0. So it turns out to be this phasor VR equals to IR times R. Okay, we just skip over all the cosine. Okay, so it's just like a normal Ohm's law. It looks like an Ohm's law. This is what we would like to find. Okay, finally, we have a RLC circuit, but with a single frequency sinusoidal, then we can just play with the generalized Ohm's law. Okay, so in that case, we consider the impedance of a resistor. The impedance of a resistor is ZR equals R. So it's nothing but the resistance. Okay, impedance in Chinese is called 阻抗. Okay, so this is the easier case. So you just consider V equals IR. Finally, it becomes V equals IR. Okay, nothing special. So here, this is the next thing. Okay, is the capacitive load. So we consider we connect a AC source with the capacitor. So here still E is EM times cosine of omega dt. Okay, of course, still this is VC. VC should be the same as E. So VC is VC cosine omega dt. But I is not just a division. Okay, so IC, this is IC should be CD VC dt. Okay, IC should be CD VC dt. So we just plug in this one here. So here we have C times VC. Okay, this is C, this is C, this is VC, this is VC. And then we should take the derivative of the cosine. Take the derivative of the cosine becomes negative sine of omega dt. And then also we should have the chain rule. Take the derivative of the argument omega dt. So this is the first order. Take the derivative becomes omega d. So this is due to the chain rule. So negative omega d CVC sine of omega dt. Okay, later we still try to change it back to cosine. Change this back to cosine, so that we can just compare this one, compare the phase between this one and this one. Okay, so in high school trigonometry, you know cosine of x plus pi over 2. Cosine of x plus pi over 2 should change to sine of x but with a negative sign. So here we have negative sign becomes cosine of this one plus pi over 2. Okay, so we know that we have a 20-degree phase shift between this one and this one. Of course, the amplitude is different. Okay, but anyway, if we try to define something like so which means that this is the amplitude, this is the phase, which means that we have a VC to be VC. This is VC, the phasor, VC with 0 degree, and then IC should be something like omega d C VC, and then exponential to j pi over 2. We change it to a complex number. Okay, using this phase and the amplitude. This pi over 2 go to here, and then this is the amplitude. Okay, so exponential to j pi over 2, what is it? Exponential to j pi over 2. If you still remember, cosine of pi over 2 plus j sine pi over 2. Okay, this is 0, this is 1. Okay, so this is j. Okay, so this is j omega d c vz. Okay, this is IC equals this one. Okay, so we try to move this thing over. So we have something like Vz equals IC and then times 1 over j omega dc. If we assume this one is the impedance Z, okay, so we just make this one ZZ, the impedance of the capacitor, to be 1 over j omega c. Okay, so yeah, here is omega d, so but generally we can just write it as a j omega c, 1 over j omega c. So this is the impedance of the capacitor. Okay, if we just put in here, it becomes Vc equals ICZZ. Okay, it also looks like the V equals IR form. This is what we want. We hope even for RLC it have the same thing, but it depends on CZ is 1 over j omega c. It's just complex number and actually a pure imaginary number. If you just move this j to the top, it is like a negative j over omega c. But usually I will use it like 1 over j omega c. Okay, so it is an imaginary number. Okay, so similarly for the inductor, we also get assume this ACE source is E equals EM cosine omega dt. IL is IL cosine omega dt, and then we just take the derivative because VL is L di dt. So we put this one here. So L move to here, IL move to here, and then cosine, take the derivative of cosine becomes negative sine, and then the chain rule for this one, omega d comes out. So we have a VL equals negative omega d L IL sine of omega dt. Similarly, we can just make this negative sine of something becomes cosine of omega dt plus pi over 2. Okay, so here we also considering that let's say, so this VL is VL, and then okay, this one is actually omega d L IL, and then exponential to j pi over 2. So actually j pi exponential to j pi over 2, this thing is actually j. So it becomes j omega d L I L. Okay, so here we consider this one to be the ZL, this one to be ZL. So if this one ZL is j omega dl, it becomes VL equals ILZL. So this is our objective. We make it like VL equals ILZL, VZ equals IZZ, VR equals IRZR. Okay, of course, this ZR is nothing but R. This ZZ is 1 over j omega z. This ZL is j omega L. So we need to make this transformation, and then finally we will get this thing. Okay, all of them look like the Ohm's law, but with a complex number. So z is a complex number, zz is a complex number. This is a complex number, but it is only a real number. But if we have the series, we can just add them together. If we have parallel, we can just multiply and take the reciprocal, add them together, and then take the reciprocal again. So we can apply many of the formulas we have learned based on this assumption. Okay, so let's